In this video, I'm going to be going through reactions, and normally I like to have some sort of theme song for reactions, but I couldn't find anything I really liked for reactions, so I just found reaction videos. I do particularly like Kids React to Chuck Tester got turned into a Songify song, which is pretty good. But yeah, if someone comes up with a good song, I mean, like there's songs about chain reactions, but anyway, if someone can find me a better thing, I will take it. So what we're looking at is at the end of bridges, we have the things that the bridges sit on called reactions, or supports is probably the term that we would use. But what we have talked about before is that when we apply a force onto a chair, there's a reaction force that stops us falling into the ground. Well, bridges are the same. So that bridges have mass, and under gravity they have weight, and on top of that there's loads that apply to them, mostly the mass of vehicles and things that are, but also wind loads, and those forces need to be transferred to the earth somewhere. And so they in order to maintain equilibrium, where that force is transferred to the earth, there's an equal and opposite force that holds the bridge up called a reaction force. Now, at the HSC level, we will only ever deal with two different kinds of reactions. We'll either I guess three different kinds of reactions, but when we look at them, they're going to be in groupings, two different kinds of groupings. So we're either going to have what we call a pin and roller, or we're going to have a single fixed reaction. That's the only two situations that we'll deal with at the HSC level. Now, when you get to about third year uni, you do start dealing with more complicated situations where you find out that not everything is technically a pin or fixed. There's there's somewhere in between those things. You learn about multi-span bridges that can have multiple reactions. But for HSC level, it's already more than complicated enough. So we're just going to focus on one of two scenarios. So the two scenarios are that we're either going to have a bridge with two different reactions, or we're going to have a single cantilever. So I haven't bothered trying to look, but we'll have a look for let's have a look. So there's a kind of bridge called a cantilever bridge. It's not what we're really talking about here. Cantilever bridges are important and interesting design. What we're interested though in is just cantilevers. A cantilever is when we have something sticking out over the edge of the reactions. Now, this picture here shows three different scenarios. We can have just a bridge with, or a beam with something sticking out over the edge, or we could just have one reaction. So here we have two reactions, but I don't really like that picture because that's not what we'd use in the HSC. But we have a house here where the house is cantilevered out over the front. So the cantilever has a free end. So that's what we're going to talk about. A cantilever at the HSC level will always have to have a fixed reaction. But yeah, the place where we most come across, I mean, this is an example of something that's cantilevered, but the main area where we see cantilevers is balconies. Balconies are often cantilevered, where they extend out past the walls which serve as the reactions. Okay, so now that we've got that terminology, let's have a look at what there's three different kinds of reactions. Now, we have rollers, so that rollers are the simplest. And you can imagine that rollers help keep the bridge up. But if we had rollers on both sides, if you were to push the bridge, like even just a little bit, the bridge would slide, and that would be bad. So what we need to do is we need to have one side, what we have is one side that can roll, but then we have another side that doesn't move. And it's not fixed, right? Instead, it is, and I had the word here already, pinned. So the Harbour Bridge, it doesn't have rollers, I don't think. I mean, I'm not a specialist in the Harbour Bridge, but my understanding is that on the south side it looks like this, and on the north side it looks like this, and there's no roller. There's it gets rid of it doesn't need to have the roller because it has a third pin, but that's definitely beyond the scope of this course. There's a pin in the center. But what most will have is they'll have a pin at one end and they'll have a roller at the other. Now, the reason why we need the roller is so that we can accommodate for thermal expansion. So that's why we need the roller at the other end. Now, instead of that, we can have a fixed reaction, which we saw cantilevers. Let's see if we can see fixed supports, maybe. Yeah, so a fixed support is where something is bolted hard into the wall. Now, we would call that, at third year, we'd say that that has a high level of fixity. So it's somewhat pinned, but it's mostly fixed. But if it's concreted in, that's a fixed support. Yeah, when it's embedded, when concrete is embedded into the masonry of the walls, that would be a fixed support. Okay, so we've now got that terminology. Now, we use symbols to refer to these, right? So in my notes, MIT has some lectures where they have the different symbols for these kinds of reactions. Making a liar out of me. Okay, there's different ways that we can show the reactions. Fixed, pinned, roller. Okay, there's different ways that we can show it. This shows, here we go, this shows two main ways. Yeah, those two are pretty good. Okay, so this way here, this is very common, is we draw them as triangles with, if they have little circles underneath, they represent wheels that roll. Or we can show it as pinned, as just having the triangle, and fixed we usually show with a couple of lines to show the masonry or the concrete wall that represents the wall. Another way, and especially computer software, tends to show it as rollers just simply as a circle, pins as a triangle, and fixed as just a straight line. Now, what we're interested in is, I'm going to show you the standard symbols that we use in a second. But what we need to know is that rollers, they can only provide a very simple reaction. They can provide a reaction that is generally straight up, but it's not up or down, but rather it's perpendicular to the surface that it's on. It's a normal reaction. A pinned reaction can have a horizontal and vertical component, which we think of as being a diagonal component, and then fixed supports. So for things like a cantilever, in order to stop the beam from spinning in a continuous loop, what we need to do is we need to have a moment reaction. So when we talked about moment couples, I'm not going to go into too much detail until we get to bending, but there needs to be a bending moment in order to maintain the equilibrium in a fixed reaction. So now that I've said that, that's the technical terminology. I'm going to show you a picture that I made to sort of help explain this and a mnemonic. So I've personified these three different reactions, and I've drawn the symbol that we typically use. Now, I should say that rollers don't need to literally be on wheels. They can just be two plates lubricated with graphite. That's an alternative way of having bridges, but as the bridge gets larger, you need larger and larger bearings. So it is more likely for a full-scale bridge to have actual wheels that it rolls on. But, okay, so we've got three different... I personified these reactions as Ricky, Penny, and Victorka, and I tried to show the level of complexity so that we have Ricky as the least complex and Victorka is the most complex. So the idea is that Ricky, well, so she's on roller skates because she's carefree and she only has to worry about standing up, about maintaining a perpendicular force. That's it. As long as she can support herself, if someone tries to push her, like the Matchbox 20 song, well, then she's just going to keep going in that direction. She's not going to resist. She's just going to be, she can be guided, and that's what we expect for rollers. They can't push back. Penny, on the other hand, so I'd like to think of Penny pushes back. So the pinned reaction pushes back. And so how we represent this is, rather than, we don't show the little wheels, we just have the triangle, and Penny can have both perpendicular and parallel forces. And so by saying that Penny likes or can deal with both perpendicular and parallel forces, what that means is it just can mean it can have a diagonal reaction. And then finally, I have Victorka, and I like to think of Victorka. She's grown up in Russia in the hard times, and Victorka, she's the most serious. She's she's seen a lot, and she can deal with everything. So she likes all forces. She can take, not only can she take perpendicular and parallel forces, or what we'd call that diagonal forces, but she also can handle or likes moment forces, moment reactions. And I just find this image helps me when I'm trying to remember, when I say out loud, is this the pin or the reaction? The image of Ricky on the roller skates helps me to remember that rollers have little circles. That's really the one that I focus on. I don't have trouble remembering fixed reactions. That one I can remember without too much hassle. I try to show that she's stick thin because in Russia there's not always enough food. But just to remember, I often find that I forget when I'm saying the words out loud, even though I know internally what they mean, when I get to say the words out loud, I can sometimes get caught out. And thinking of Ricky on her roller skates helps me to remember. And if not, there's a video that I could share with you. Anyway, okay, so what we've got next is we have the book. The book has in table 1.1, so this is the first table of chapter 1. It has the same symbols that I showed. It shows the circles a little bit bigger than I would say you typically see at a university textbook, but you know that's still represents how we represent fixed pin or roller reactions. Now, it's important that when we look at roller reactions, there's a tendency to say that they can only provide a vertical force. That's what we tend to say. The thing is, that is not true, right? So they don't only provide a vertical force. In this situation, we have a truss. By rotating this truss has got a crane supported on it. In this case, what we're going to have is, in order to balance this force, the reaction B is going to be pushing out to the left, like Beyonce, and reaction B is going to be pushing left, and it's parallel to the wall. Sorry, I just said parallel. I said the wrong thing. I'm not going to edit it out, but I'm just going to instead hit my head and say, bad Luke, and say it's perpendicular to the wall. The force is coming up perpendicular to the surface of the wall. Now, in that case, reaction A, well, it has to be going upwards because it's the only one that can respond to this. If horizontal force, if this B is putting out a horizontal force, well, something needs to provide a horizontal force to the right in order to cancel out Beyonce. So A is going to have to be going to the right, and then we have a downward force that needs to be cancelled. And B can't take that because B is a roller. B can't provide that force. So it means A is going to have to be providing that force. So A is going to be going up and to the right. And so when we have these sorts of questions, right here, in this case, we have this force, because it's a roller, it will be vertical, only because the surface that it's perpendicular to is horizontal. In the case of reaction B, well, we don't know the angle of reaction B. It's going to have some amount of vertical component and some amount of horizontal component, and it will be a diagonal force in some direction. We don't know what that direction is. We can't use the three-force method because there's too many forces on this diagram, so we're just going to have to work through it, and that's in the 2012 paper. We then have this one here is, I think this is a trial question. It could be from the 2000 papers. They're older papers. So here we do have a roller, and this roller you can see is at 45 degrees. So that means the reaction is going to be going 45 degrees up and to the right. And once we know that we have that reaction, then we can find that's a reaction support A and D. Yeah, 5 marks for that. That's okay. It's a harder question, but it's worth 5 marks. Okay, this one's exactly the same. A is going to, this time it's A that's pushing to the left, and B is going to be up and to the right in order to maintain that equilibrium. Okay, so that's, when we talk about parallel and perpendicular, that's what we're talking about. Rollers are always perpendicular to the surface or normal to the surface, regardless of the surface. So it could be pushing to vertically, or could be pushing horizontally, or it could be pushing it 45 degrees. It all depends on the surface that it's responding to. Typically, 9 times out of 10, maybe even 99 times out of 100, it's going to be a vertical force, but it's worth noting that sometimes it's not. Now, when we solve trusses, when we find reactions, so most of the time you can see here that these are all trusses, right? Now, I've spent a little bit of time in the history of bridges talking about trusses. Tom Ugley's Bridge is a bridge that's relevant in southern Sydney. If you live in St George or the Sutherland Shire, you should be familiar with Tom Ugley's Bridge. But they're trusses. I also spent some time this morning talking about roof trusses. But to start off with, we're just going to work with a simple beam and calculate how we'd find the reactions of a simple beam. So here I have Copeland's book where they've got example 1.1. I don't remember what page number this is on, unfortunately. But I have already gone through this on this video. Now, unfortunately, the lighting is not fantastic, but at least you can see, you know, when you zoom in, you can see what's going on, I guess. But I have gone through this one, but I will go through it again quickly. I have not gone through the second example, which is this one here. So I will focus my attention on this second example. So this is really for people who ideally have watched this other video and haven't understood it, but I'm going to go through that with the worked example. I will go through the other one very briefly. Now, after that, we do have two more examples in the textbook, which are very, very similar, right? We can see that one's very similar, just the difference in that direction of that force. So A is, the force is going up, not down. And the second one is pretty similar to this here. The difference is there's an additional force, and the load condition is a little bit different. Okay, so I have videos that go through both of those answers, right, for both of those. So I don't need that. I think I just closed 1B. Okay, now as for cantilevers you don't see many questions on. There's one question in the textbook, question 18, it does talk about cantilevers, and we have this guy walking like an Egyptian. And then we have, from 2009, there was a question that sort of talks about a cantilever, that effectively this is a cantilevered force. It's a bit of a tough one. Effectively, because there's only one reaction, they've combined it as reaction B. They've considered that it makes this a cantilever force with a big turning moment that needs to be counterbalanced. This question here, this is a more recent one. I don't know, it's from the last 5 years, so it's somewhere after 2015. This question is there we go, 2015 is almost certainly when and it's question 15, so I don't know, I'd say it's from the last 5 years. It does, talks about cantilevers, and then we're back to the textbook. Okay, so I'm not going to focus on cantilevers. That we really worry about cantilevers more when we get to bending. So reactions are critical for not only for trusses, but they're also critical for bending. Now, I think trusses are the most likely thing to be in the HSC exam. They're almost certainly going to be worth 2 marks just for reactions on their own. Trusses are typically worth, I'd say statistically, between 3 and 4 marks. And then bending statistically is worth somewhere between, I'm going to say 2 and 3 marks. In that there have been 6-mark questions on bending, but there haven't been 6-mark questions consistently. It can be anywhere from 1 to 6 marks. For a few years there was no bending, and then I like to think that I was the person who brought bending back by complaining and saying that bending is the most important skill. Being able to design for bending moments is the most important skill for civil engineers, and I would have to assume it would be the most important skill for mechanical engineers as well, or certainly right up there for mechanical engineers. Certainly for civil engineers, way more important than being able to solve a truss. Now, we don't need these trusses, so we're getting down to the nuts and bolts here. So we've talked about the different kinds of reactions. I'm not going to read these out because I think I've already explained everything that I needed to talk about. But I guess I'll give a quick analogy to say that if we have, as an example, if we had a metal ruler and I put it between 2 fingers, then in that case, we'd say that each finger is kind of acting effectively as a pin reaction. Now, when you start to get a horizontal component, in that case, they start to have more. Pin reaction is probably reasonable. But if I want to instead have the ruler supporting a weight and it's held off the edge of a table, this is all hard to say without actually having a camera and a ruler, then it's behaving more like a fixed reaction. But again, I don't want to really go too deep on fixed reactions for the moment. We're just going to start off with the method that we should use in the HSC to solve these questions. So the thing is, there's much like, I don't know if you guys remember, Giggle and Hoot had their 5 steps to bed. That there were 5 steps to sleepy time. We have 5 steps for finding reactions. So I'm just going to get exercise 1. Okay. So the 5 steps are, First of all, you want to simplify the diagram from a space diagram to a free body diagram. Now, last year you won't remember the picture of the three people walking like an Egyptian over a wooden log. Well, what we want to do is we want to take out all of the bricks and the trees and all of the other distractions, and we want to simplify the diagram down to just simply forces and members. So members being the distance between objects. Once we've done that, the next thing we want to do is we want to turn everything from, we want to take away all the diagonals, and we want to turn everything into horizontal and vertical components. Now, this step is not always required, right? Sometimes you might want to say that, hey, the provided distances or the drawing is drawn to scale, and I'm just going to take those dimensions. Take those dimensions, but there is a good reason why you always want to approach it from the attitude of I'm going to always turn diagonals into horizontal and vertical components. That is a good strategy. Part 3, you always take moments about the non-roller first. So another way of saying that is you take moments about the pin because you want to find the roller, right? You want to start with simple Ricky the roller and then find complicated Penny, right? You don't want to go the other way around. Now, you could if you wanted to, but it's certainly not the way that you'll see me do it. It's not the way that you'll see the textbook do it. And the reason why you don't want to do that is because it gives you just a clear direction for where to start, but also, look, I will say again, there are exceptions to every rule, and there are reasons why if someone says to you, find reaction A, and reaction A is a pin, well, in that case, you don't need to find reaction B necessarily. But because Penny the pin has 2 parts, right, you need to do more work to find the pin. So if you have to find both, start with the roller reaction because that's going to be faster. Now, once we found the pin, then we can use the sum of the forces vertically and the sum of the forces horizontally to find Penny. That's typically how we'll do it. So what we'll do is we will take moments, right, the sum of the moments about the pin to find Ricky the roller, and then we'll take some of the forces vertically and horizontally to find Penny. Okay, and then lastly, and this is I think something that really slows down a lot of people because they don't do this in practice, is finding not just the components of Penny, right? Not just finding the vertical and horizontal components of the reaction, but then actually using trigonometry to calculate the angle and Pythagoras Theorem to calculate the resultant of those two horizontal. So here we have a horizontal and vertical force in this pin. What we need to do is we need to actually take Pythagoras to find the the resultant of those two forces, and we need to use trigonometry. So we use tan opposite over adjacent to calculate the angle. Okay, so that's the 5 steps. So let's go through those steps really quickly. So the first thing we're going to do is we're going to simplify the drawing. We're going to create a free body diagram. The next thing, we're going to turn the diagonals into horizontal and vertical components. We're going to take moments about the pin to find the roller. Once we have found the roller, we're going to use some of the vertical forces horizontally and vertically in order to some of the vertical forces and some of the horizontal forces to find the pin. And then once we've found the components of the pin, we're then going to find the total reaction and the angle of that reaction. Okay, so let's have a look at this question here, where what we've been asked to do is we've already been given a pretty good diagram. Right? I don't personally feel the need to simplify this diagram down, but what they've given us is a little bit of a visual diagram. Obviously, they've done some abstraction, right? These reactions didn't probably look like an actual triangle. But what we've done is we've replaced that with just the forces and the members. Now, another thing to note is that because each of these 3 forces is exactly the same distance, we don't need to necessarily worry about using meters or kilonewtons or newtons. It doesn't really matter what units we use for distance and force because everything will cancel out in the end. So as long as we're consistent, it doesn't really matter if we use meters, if we use 10 meters, if we use pi meters, like 3.14 meters. It doesn't matter what units we use as long as we're consistent. As long as everything is divided by the same amounts, they will all work out at the end. Okay, so what we've got now is, first of all, so step one, we've simplified the diagram. Step two is we've taken this 30 kilonewton force, and it's at 45 degrees, so we've said 30 sine 45 and 30 sine 45. We've taken away this diagonal and we've turned it into a horizontal and vertical component. Now, what we can do then is we're going to find Ricky the roller by taking moments about A. Because A is the pin, we're going to find the roller, so we're going to find reaction B. So if we measure everything from reaction B, how many forces do we have on this diagram? Well, as far as we're concerned, now that we've converted this diagonal into a horizontal and vertical force, we have 1, 2, 3, 4, 5. Now, I want to point out that often they don't even bother to show this force or this force. They don't bother to show this or this force in the calculation. Why don't they show reaction A? Well, reaction A is 0 meters away from A. Anything multiplied by 0 is 0. Now, why is that important? Well, moments are equal to force times perpendicular distance. If I say that A passes through point A, the line A passes through point A, well, the perpendicular distance of line A is 0. The same way that if I have 30 cos 45, if I tell you that it passes through point A, which we can see it does, it means that it's going to also multiply by 0. And effectively, it's going to have 0 effect on the turning moment at point A. So we can ignore those in our equation. So what we have here is the sum of the moments about A. So this is saying the clockwise, sigma for sum, m for turning moment, measured from point A. That's what this equation means. Clockwise, the sum of all the moments measured from point A equals 0. Now we know that that's true because otherwise it wouldn't be an equilibrium. If you're not sure what that means, you need to let your teacher know, because that's a year 11 concept and you should be familiar with that. Okay, so then what they've said is they've broken this down into 50 times 10. Now where's 50? 50 is 50 kilonewtons times 10 meters. But you'll notice that they've ignored this force. Now I like to usually write down RA times 0, but they haven't done that. They haven't written RA times 0 because it's 0, so we can just move on. And then they have 30 sine 45. Now how far away is that from A? Well, it's 10 plus 10 away. A lot of people, an enormous number of people, will just write down 10. They don't write down 10 plus 10. So we can see that that is 30 sine 45 times 10 plus 20, which is 20. Now, I usually like to write these in brackets. I write 50, open parentheses, 10, close parentheses, plus 30 sine 45, open parentheses, 10 plus 10, close parentheses. That's how I usually do it. I tend to write, rather than writing 30 sine 45, I'd write 30 brackets, 0.707, close brackets, open brackets, 20, close brackets, 20. That's how I would usually write it, but I understand what they've done. Now, you also notice they've ignored 30 cos 45. That didn't even make it onto their equation. Why? Because it multiplies by 0. Then finally, they have 30 RB. Now, why did they say minus 30 RB? Well, if we're putting a pin on A, if we put the axle of our wheel is centered on A, if we push down on this wheel, if we mention if it was the hands of a clock and we push down on this hand of the clock, it's going to turn this clock clockwise, and this one is also going to, at least the vertical component, is going to push also clockwise. So you can see both of those forces are turning the wheel clockwise. But B, on the other hand, B is turning the wheel anti-clockwise. Now, if we have a look at this description here, no one told us that B is going up. We know that B has to be vertical based on the fact that it needs to be perpendicular to a horizontal surface. But no one said that the reaction at B was going to be up. All they said was going to be vertical. We made an assumption. That B was going to be up. So based on the assumption that B is going to be up, we can say, well, if it's up, then it's anti-clockwise. And if it's anti-clockwise, then we're going to notate that as negative. Now, I should point out that I always, in my classes, always use clockwise as positive. I didn't always do that, right? When I worked professionally, I would do 50-50. I'd go clockwise or anti-clockwise, depending on the circumstance. All through uni, did the same. When I was in high school, did the same. But when I started teaching, I just said, you know what, I'm going to always be consistent and I'm always going to use clockwise as positive. So sometimes you'll see HSC questions where they say anti-clockwise is positive. And that's just because you're allowed to assign whatever convention you want. But I personally use clockwise as positive. So I often write a lot more, and you'll see me in my other videos discuss this a lot, where I will write down, we've written this down as 0 equals RA times 0 plus, and I would have made the sound effect where I go da 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 da, where I try to figure out if it's going clockwise or anti-clockwise. So I'd write plus 50 brackets 10 plus 30 sine 45 brackets 20 minus RB brackets 3 times 10, because you can see the reaction of B is 3 times 10 meters away. Now, what we could do is instead we could do this in units of 10. So we could just write 50 times 1 plus 30 sine 45 times 2 minus 3RB. That would be exactly the same. It would have no difference on our equation because our answers will work out the same. You'll also notice we're using kilonewtons. We're not using newtons. And again, that's because multiplying or dividing the whole equation by 1,000 doesn't make any difference to the end result. As long as we're consistent with our units, it's all going to be okay. And then we say RB, so that this is the reaction at B is equal to this number divided by 30. So I'm not going to go into that year 9 algebra. I'm going to assume that you know that year 9 algebra. We're going to move on. Now, because this number was a positive number, that means our assumption was correct. If our assumption was incorrect, that we would get a negative number, and that would mean that the reaction was actually down and not up. This does happen, especially with cantilevers. It's very possible that with a cantilever, it is possible to have an equation where you have a force, a reaction that is going down and not up. Okay, so now that we've found RB, what we need to do is we need to find RA. Well, okay, so what we know is how much downness do we have? Well, what we have is first of all, I'm going to take 0.707 times 30, right? So we've got 21.21 down, and we also have another 50 down. So we've got 71 down, but then we've just found that combating that 70 down, we have minus, or in the opposite direction, 30.8 up. So there needs to be an additional 40.41 up in order to balance this. If we don't have 40.41 up, the thing won't be in equilibrium. Now, we've got 40.41 up. The question then is how much, we know that A is going to have some sort of horizontal component, right? Because it's a pin. How much horizontal component is that? Well, we can say of all of these forces, we said that we identified 5 forces. 1, 2, 3, 4, 5, because we converted the 30 into these 2 components. There's only one force that's horizontal, right? There's a force here, but again, this diagram should really show that RA is not straight up. RA has a RAH and RAV. So RAH is actually going opposite to this. So if this is going to this one's going to the left, and then so this one here will have to be going to the right. Okay, so here we can see that this reaction A has to be going to the how much is going? It's exactly the same. 30 times 0.707, which is 21.21, which we can see here. So you have 21.21 plus 40.40 gives us this triangle. Now we could just draw the triangle. We're allowed to draw the triangle and just measure the distance, but most people will use Pythagoras Theorem. Now the important thing to remember is that the hypotenuse must be bigger than the other sides, right? If the hypotenuse is not bigger than the other sides, you've done something wrong. Obviously as well, it can't be bigger than 60, so it has to be somewhere between 40 and 60. Now we've got 45, that's right where I'd expect it to be. But obviously it can't be bigger than the sum of these 2 sides, right? So just to try and give us a bounded range, that it has to be between 40 and 60, right? So that gives us a way that we can estimate. And also when we draw this picture up, we can have a look at the angle theta, right? Now I would have drawn theta a little bit closer to the corner, but the angle theta, it looks like it's more than 45 degrees. That makes sense because it's taller than it is long. So that means that we're going to have some idea that it's going to be greater than 45 degrees, but obviously less than 90. So that helps us to say, okay, well, it's 62 degrees. Now, I am not going to go through the maths of how to do these calculations, Pythagoras and calculating the angle. There's plenty of worked examples on my YouTube where you can see that in greater detail. But for the moment, if you don't know how to use that function on your calculator, you probably need to let me know and I will go through it with you. Or you need to let your teacher know and they will go through it with you. So that gives us our full answer. Now I'll note that typically we usually want to measure our angles from the horizontal. If you're a surveyor, you measure from north. If you're doing anything else, you typically want to measure your angles from the horizontal. So you can see that that's what they've done here. They've given the angle as 62.3 degrees, not as 27.7 degrees, right? They've given us the not the larger angle, they've given us the angle that is measured from the horizontal, and that is typically how we do it. I think I talked about that in year 11 right at the start. Okay, so now what we're going to do is we're going to do the same thing for question 1.2, and that's where I'm going to leave this lesson at the end of this, because this is the one that I haven't given a worked example for so far. Okay, so remember there's 5 steps, right? Okay, so there's 5 steps that we're going to do. Step 1 is we're going to draw our diagram as a free body diagram. Now again, this diagram looks pretty good, so I don't need to worry too much. But what we're going to do is we're going to replace our reactions with forces. Now, we should note here that this one I like better because here they've actually shown RLV and RLH, right? So it's important that they've identified that this pin has 2 parts, right? So Penny, she's got 2 parts. So the other thing they've done is they've converted the 250 newtons to 250 sine 30, which is going to be half. That's going to be 125. But I do have a scientific calculator, but I'm not going to go to the effort. Am I going to do that? It's like 30 degrees. There you go. 30 degrees times 30 is 0.5. And this cos 30 is 0.866. 0.866. Okay, so 0.866 times 250. Oof. Okay, it gives us 216. Now, they've written it down as 250 cos 30. That's fine. But we just want to know that it's 216, right? So what we've got is the next thing we need to do is we don't have any distances, but what we do have is we can make a reasonable assumption that this Warren truss has each of the triangles is an equilateral triangle, and all the triangles we tend to deal with are going to be 60 or 45 degree triangles. So that makes our calculations quite easy. Not easy, but at least consistent. And that's why I've gone to the effort of memorizing what cos 30 is. Okay, so what we need to do is we need to calculate, well, what is this perpendicular distance? If we're going to measure from reaction L, what is the distance to this force? Well, what we've done is we've said that we're going to let this side, the side of each of these, be 1 unit long. Now, sometimes you could write it as 1 unit, but they've written it as 1 meter. That's fine. It doesn't matter. As long if it's 1 meter or if it's 35 meters, it doesn't matter because we're going to multiply everything, but it all cancels out in the end. The same way as it doesn't matter if we use newtons or kilonewtons, it all as long as we're consistent, it will all work out at the end. But if this was 1 meter, well, then if we were to cut this in half, what we would be able to do is we'd be able to say that if assuming it's 60-40 triangle, trig identities, right? So if this is 2 units, this is root 3 units. So root 3 is 1.73. Divide that by 2 gives us 0.866. Now, another thing we're allowed to do is typically in the HSC, with the exception of 1 year that I can think of, in 19, 18. In 2018, the HSC said not drawn, not to scale, something along those lines. And I can tell you from discussion with experienced markers that if you had answered the question, if you'd solved the question by drawing the question to scale, you would not have lost marks. Even when it explicitly said in that particular case, right, for trusses, you can pretty much assume that it's going to be drawn to scale. That's what we're going to look at. So what is the perpendicular distance now? If I wanted to, I mentioned earlier that not every time you want to follow these 5 steps, sometimes you don't want to find the perpendicular distance. You don't want to find the, you don't want to break this into components because it's just easier to find, I already know the perpendicular distance of this because of the angle, right? Vertically opposite angles are equal, so they've alternate angles and vertically opposite angles. Alternate angles on parallel lines are equal. Sorry, I got a little carried away there. So we can see that if this angle is 60, well, that angle is 60. 60 plus 30 is 90. So I know the perpendicular distance of this force is 1 meter. The problem with that is I'm going to have to break it down anyway. So if I'm going to break it down anyway, I might as well just use the component forces. But your mileage may vary, right? So for me, I often will measure perpendicular distances without converting into horizontal and vertical components. But if we're going to follow the 5 steps to bed, the first step is free body diagram. Second step, remove diagonals and get horizontal and vertical components. The third step is take moments about the pin to calculate the roller. So if we're going to take moments about the pin to calculate the roller, let's see. We're going to take moments about the pin. So we've said some of the moments about. I don't like that they didn't have a letter there. They needed to say some of the moments about any. It's true that it doesn't matter where you take moments about, it's equal to 0, but we want to specify to help our marker to know where we're going. And we can just label things. We just label this as L, right? So what we're going to say is 0 equals 250, which we said was 216.5 times 0.866. So that's is it going clockwise or anti-clockwise? So that's going clockwise. Now, you'll notice that we also ignored RL. So I would have written RL times 0 plus 216.5 times, or brackets, 0.866. And then we've got 250 sine 30. So, okay, so we said that that's 125. 125, and how far away is it? It's 1 triangle away. So if we extend that line down, we can extend that line down. The point where it is perpendicular is here, right? If we draw, I actually find it helpful, and sometimes I do this in class. I actually get a set square, and I say, where is it perpendicular? I say it's perpendicular here. And what is the distance? It's half a triangle away. So it's 125 times 0.5. And so just so that we can see that we're getting, we've got 0 times anything is 0, so we don't even bother writing that down. We've got 216.5 times 0.866, which we just called 187, movie with Samuel Jackson. And then we've got 125, because this is already 250 times a half, so 125. 125 times a half. 125 times half is 62.5, that sounds right. And then lastly, we have this, we have 2 more forces, sorry. We have 225. How many triangles away is it? Well, it's 1 triangle, 1.5 triangles away. So the distance here, if we extend this line down, where is it closest? Where is it? It's going to be perpendicular where it's closest. If we extend that line down, the point where it's closest, sometimes I actually get a window, just a second. Usually what's easiest is to actually just get like a set square on the board. But in this case, what we'll do is say, well, okay, if we just draw that down, right, the point where it's closest is here. That's where it's perpendicular. How many triangles away is it? It's 1.5 triangles. So half a triangle, 1 triangle, 1.5 triangles away. So you can see that's why it's written 225 times 1.5. 225 times 1.5 is 33.75. Okay, cool. And then they've got minus 2RR. So let's have a look. So it's 2 triangles away. That makes sense. And the force, reaction R, is going anti-clockwise. So that's why it's a negative, because it's going anti-clockwise. Anti-clockwise. That's why it's a negative. So what do we get? We get 587, which is these three numbers added together, divided by 2. Now that we did a bit of algebra there. If you watch my other videos, I probably have gone into painstaking detail where I've actually added 2 to both sides to keep the equation equal. But most people are pretty good at that by year 11, or by the tail end of year 11 when we're into HSC content. Most people can do that level of algebra. Okay, so once we've done that, we've then able to find, what we've found is the value of Ricky the roller is 293. Now, if we know that that's 293 up, well, okay, let's measure what are all of our vertical forces. We've got this, which is unknown. We've got going down, so we usually write that as a minus, right? So if we right here, we said sum of the forces vertically with up as positive. So what we're going to write is we're going to write RLV, the reaction at the left-hand side vertically, minus 125 minus 225 plus 392 equals what? Okay. So if we move the equation over, what we can do is what it'll do is reverse it. So what we've got is 29375 minus 250, right? Because that one's going up, so it's positive, minus 125, right? Minus 125 plus RLV. So what we get is, look, I trust Copeland's calculations, but it may help for you to see it. It may be beneficial. So they've said 293, it's going up, so it's positive, minus 125 minus 225 equals 57. Now, the reason they've given a negative answer is because the LV has to come over this side to balance it out. Okay. Now, there is only one pair of horizontal forces. There's this, remember we said 50 cos 30. We said that was 216.5. So if that's 216.5 going to the right, then this here is going to have to be 2165 going to the left, right? So that's where we get, you can see here we've got our diagram now, 2165 and 50. Now, straight away, I can tell you that my angle is going to be, my reaction is going to be, without looking, it's going to be a bit more than 216, 220, 230 max. I can tell you that the angle, without looking, is going to be less than 45 degrees. And it looks comfortably less than 30 degrees. So how do we calculate that? Well, we use Pythagoras Theorem. We say 56 squared plus 2116 squared, take the square root all of that, gives us RL equals 223. And the angle, so we're going to say, well, tan equals the opposite over the adjacent. So the opposite of the angle, remember that we always like to measure from the horizontal. The opposite of the angle is 56 divided by the adjacent, which is 216, which gives us 14 degrees. And then we write the reactions like that. Okay, so that will do for this video. We're going to go into trusses next week, and trusses are even more complicated than this. So it's really important that we have reactions down. Now, I will tell you that I have seen classes where I did a prac at the end of the term, and at the end of term 3, where people still did not know how to do reactions, like simple reactions. When they were studying for their trials, they just hadn't learned reactions. And I will say that it's not going away. You know that it's going to be in the test. It is the thing that is most reliably going to be in the test. This is the thing you need to focus your study on right now, because it's not going to go away. You have to do this work sooner or later, so you might as well learn it and internalize it now and overcome this, because there's a test at the end of term, and in that test at the end of the term, we're going to be, that's actually next term, but there is going to be a test on this, and you need to be prepared for it. You need to know, because if you're going to get, it's going to affect your assessment mark if you don't get it now. It's definitely less valuable to you if you learn it before the trial, and it's even less valuable to you if you learn it after the trial. Okay, so that's my video. I hope that was a benefit for people, and have a good weekend.